For our second talk, we have Chris Bretherton, as Laura mentioned. He's an emeritus professor of atmospheric sciences and applied mathematics at the University of Washington. He is an American Meteorological Society Charney Award winner, IPCC author, AMS and AGU fellow, and a member of the National Academy of Sciences. He now directs a climate modeling team at AI2 in Seattle, which uses AI trained on global climate and global storm resolving model output and observational data to improve climate model simulations. So, please.
Okay, well, thanks, Jane. And I'd like to continue on this theme of AI for climate, and in particular, look at this from the more atmospheric point of view. We're now trying to couple atmosphere and ocean emulators. I'd like to tell you a little bit behind the story of the atmospheric emulator that's part of that coupling, and then what happens when we try to couple these emulators and why that's an interesting thing to do in the first place. Before I get started, this isn't my work. I direct a team at the Allen Institute for Artificial Intelligence, AI2, which is also philanthropically supported by the Allen family estate. And then we work with parts of Laura's M2 Lines team as well, which was a Schmidt Foundation project, funded project. And so this is work that comes from a lot of people. So, we're building on a basis, we're building on a base of physically based climate modeling, which has come a long way, is very sophisticated and very capable, and has been totally adequate, I would say, to inform our need to do, for instance, climate related mitigation of greenhouse gas emissions, although our own president isn't listening to that. And I'd like to first talk about what it does and then sort of compare and contrast that with what we're doing in AI-based climate modeling. So in order to model the entire Earth system, namely the atmosphere, the ocean, land, sea ice, physically based climate modeling has divided that into modular components. In each component, it uses physically based equations as much as possible, and empirical relationships where not possible. It's sort of designed in that way to generalize across climates, because hopefully those physical laws will apply in future climates as well as in present. And climate here is simulated as the statistics of short-term variability of weather interacting with similar variability in the ocean, land, and ice. And so climate comes organically from simulating the entire system on its own internal timescales of variability. And for this reason, the whole approach enables what we call seamless prediction. You don't just get the mean climate out as a result of this, you get all of the things that went into that climate, in particular, all of the extreme events that affect humans and other parts of the Earth system, ecosystems, and so on. And in this sense, it's a little bit analogous to what are known in machine learning as foundation models, in that you can fine-tune basically the same model for doing a lot of different things. You can use the same model to predict weather. You can use it to predict seasonal variability of the Earth system from a known initial condition, or you can do long-term climate. And that flexibility is actually very important for the broad applicability of climate models. So we would like, if possible, to reproduce that with machine learning with some advantages. So another thing you've probably heard about is machine learning-based weather forecasts, and in particular, over the last 3 or 4 years, they have rapidly developed to become the state-of-the-art in weather forecasting. And these do not use physical equations at all. In fact, they rely on our ability to generate by fusing a huge network of global observations that are taken every day, mainly from satellites, with very sophisticated physically based models, making so-called global reanalyses, so gridded data sets that basically describe the state of at least the atmosphere on an almost hourly basis around the globe to a high degree of accuracy. So basically, these models are simply trained to predict a reanalysis from sometime in the future, say 6 hours or 12 hours in the future from the present state of the Earth's atmosphere. That's the only aspect of physics that they know about, is they know that the Earth evolves in this way. And by learning that from something like 40 years of reliable reanalysis, they've come up with extremely skillful weather forecasts, quite skillful seasonal forecasts too, when this is coupled to ocean reanalysis. And the question here is whether these can be seamlessly extended to climate like we do, to do the kinds of simulations that we do with global climate models. And on the right here is a picture just showing how far this has come. In fact, it's come further than this. So this shows what was in 2023, basically the most accurate physically based weather forecast model from ECMWF. That's the HRES line. What's plotted here is the error of that model, root mean squared error, in predicting something we like to predict in atmospheric science, the so-called 500 millibar height, as a function of the lead time of the forecast. And obviously, the further you go out in the forecast, the worse it gets. And then what's blue is GraphCast, which was at the time the leading actual machine learning-based weather forecast model. And you can see it has lower errors at all lead times. And that remains the case. At this point, ECMWF has recruited its own AI team and makes its own AI model. So that's definitely impact into a field which was previously dominated by physically based modeling. Well, so GraphCast and other models like it basically all work on the same general principle. They take the entire global state of the atmosphere, temperature, moisture, wind fields. They pass it through some kind of an encoder. They do some kind of processing, and the processing in the atmosphere consists of mixing information in the vertical to represent lots of processes like clouds and turbulence and radiation that act mainly in the vertical direction, and horizontal exchange to represent the effects of the winds blowing stuff around. They do process through several layers of that, pass it through a decoder, and get the state of the atmosphere 6 to 24 hours later. And by training a model to do this, you can make a very accurate forecast. Okay, so now we want to consider, well, what would it take to make this work for climate? So there are a variety of challenges, ranging from easily solvable to we don't know how to solve them at all. The first challenge is that if you take those same great AI-based weather forecast models, most of them are not stable or realistic if you roll them out past about a month or so. A few are, and so that's interesting. And so we are able to start with one of the ones that actually is a bit more stable. Another thing that is true about forecasting is the longer the range of the forecast, the more it depends on components other than the atmosphere. So if you want to make a week-long forecast and you know the present state of the ocean, it doesn't really matter how the ocean evolves. But if you want to make a forecast out for 3 months, or if you want to make a forecast of El Nino next year, then you care very much about how the ocean evolves as well. And so you can't just predict the atmosphere. And the longer the time scale, the more you need to know about the other components, especially the ocean, the deeper you need to simulate into the ocean. So in particular, for decadal and longer time scales, you need to have a full depth representation of the ocean coupled to the atmosphere in order to do this problem. So we have to consider then how to couple the atmosphere to other components of the Earth system in AI as well as with physics-based models. Another really big issue, and one that we do not pretend to have a full solution for right yet with this approach, is the generalizability. I mean, the real function of climate models is we want to generalize to an unseen future where we can have some idea about how much greenhouse gas we're going to dump into the atmosphere, but we have less idea about how the Earth system is going to respond. And of course, if your model is not physics-based, there are no guarantees that it's going to work. If it's, in particular, if it's based on AI, we have every reason to think it's going to fail in that situation. So the question is then, how are we going to make an AI-based emulator that can tell us anything about unseen climates? Then the last issue is we don't just want to simulate mean change. We want to simulate variability as time goes on. Is El Nino going to change in a future climate? Are we going to get, Category 6 hurricanes? What's going to happen to extremes as well as mean? So we need to simulate variability as well as long-term trends with accuracy and with reliability. Okay, so what kind of strategies do we use for emulators? Well, there are a couple of different architectures that are used. One of them is so-called hybrid architecture, where you replace or correct only parts of the model. For instance, you might replace the atmospheric component and not the oceanic component of a model. Or you might replace the so-called dynamical core, which predicts how winds move stuff around, but you might not replace that, but you might replace the other physical parts of the atmosphere. And the other approach is so-called full model replacement, where you replace everything about the model with machine learning. There's also strategies about training. So one training approach, which has been very popular and works great for weather, is historical emulation, where you use the past 40 or more years of information about the global state of the atmosphere to train your model. That's great for the present, doesn't tell you much about the future. Or if you want to try and emulate the future using some reference, you can try and emulate an existing climate model. And so now you have access to information about the future, but obviously now your emulator, in the best ideal case, is going to reproduce the model with all of its warts and biases. So in that case, your approach is not going to make you a better prediction. It might make you a faster prediction. Okay, so now I want to talk about our efforts to making a nice general purpose atmospheric emulator. So again, just like with physics-based models, we're aiming to seamlessly derive the climate as statistics of weather. So we're going to predict the weather in this case, but be able to do it for many, many years. So since we are interested in future climates as part of this effort, we can train our model on historical reanalysis, and we've done that, and it works really well for that. But we also have spent a lot of time training it on climate model output, not just for the present, but for future climates. So this then allows you to train across a variety of climates. And so the idea there is you train your emulator on a few climates, and hopefully then it'll generalize to ones in between or other greenhouse gas scenarios or flexible range of things that people are interested in that can kind of cover the basis of climate modeling. It's also actually allows you to rigorously test generalizability, because in a world where you do know future climate, in the world of a climate model, you can then also try training AI only on information you might have at present and see how well it could predict this now known future climate. So it's actually a good way to get at the generalizability issue. Our approach is simple and fast. We use a 100-kilometer grid, which is kind of typical of most climate models. We only predict 8 layers of the atmosphere, which is less than most climate models, because AI can kind of learn the relationship between different parts of the atmosphere in a more sophisticated way than the conventional climate model. And importantly, we also predict all of the energy and moisture fluxes and actually momentum fluxes between the atmosphere and the surface, and also the energy flux between the atmosphere and space. And so we can do things like energy budgets and look at energy conservation in our model. Our model runs 1,500 years per day on a single H100 GPU. So like Laura's model, it's very fast compared to a conventional climate model, over 100 times faster than a physics-based model with the same characteristics. It's fully open source. And we've applied it to climate-relevant problems of increasing complexity. So first we just forced it with an annually repeating cycle of the ocean temperature. So Laura was forcing the ocean with the atmosphere, we're forcing the atmosphere with the ocean. And in fact, the ocean is a very good forcer of the atmosphere, really keeps it in line. So this is a relatively easy test. Then more recently, we've tried to force it first with historical forcings, so to see if we can get the climate change that's occurred over the last 40 years and the variability. Then also looking at CO2 increase. And here we're trying to force it to look at future climates as well. And then lastly, I'll talk about coupled emulation. In fact, that's where I'm going to spend most of my time. Okay, so again, Laura talked about architecture. Here we're taking an architecture called spherical Fourier neural operators. It actually was developed in Anima's group at NVIDIA when she worked there by a guy called Boris Bonev. It's the same architecture that's used in ForecastNet, so we can thank Anima for this. She's walking in at the right moment. Anyhow, what this architecture does is that it does the non-local mixing of information part basically by breaking the atmosphere into spherical harmonics, which are the Fourier series of the sphere, and then allowing the information transfer in each of those Fourier harmonic components. So it turns out it's very stable, which is very nice feature of this architecture. We didn't use it for that reason at all. The main reason we used it was at the time it was the only open source atmosphere weather emulator that we could get our hands on. And it just turned out that although the first version wasn't stable, the second version, the one based on SFNO, was great and has served us very well. It's one of many architectures which you can use for this problem. It's not the only one, but it works well. So basically, the idea then is at time t, you're inputting fields of humidity, wind, and temperature at 8 levels, 8 layers in the atmosphere. You're turning this crank on it, and you make a prediction of those things 6 hours later, as well as these radiative fluxes and energy fluxes and moisture fluxes that we care about. Well, okay, so I'm not going to go over how well this works in a lot of detail, but it works well. And even our first version, what was remarkable about it was it actually captured the mean climate of that we were trying to emulate. In particular, we looked at 2 different models, one from an atmospheric model developed at GFDL and one a DOE model. But it also was able to predict extremes really well. So for instance, this is the PDF of daily precipitation. So this is at all of the grid points around the world over a period of 10 years. So it's capturing extreme events with a 10-year repeat cycle. And the original model, EAM v2, is the DOE atmosphere model, is shown in the black, and the emulator is shown in the green, and all the way out to the extreme tails it's capturing the extreme precipitation, which is really nice, not necessarily expected. Importantly for this project, though, it also, if you train ACE on the last 80 years of reanalysis, the first 40 years are less reliable than the last 40 years. If you train ACE on that, it's able to reproduce the trends we see in different climate variables. In this case, we're looking at the moisture content of the atmosphere, which is sensitive to its mean the mean temperature of the atmosphere. So it represents an effect of global warming. And what you see here in this picture is we have 3 roll-outs of ACE from slightly different initial conditions. So that's kind of random variability from year to year. And then the black is the actual reanalysis. So that's what you're trying to reproduce. This is a global integral of, or a global average of total water paths. So it's pretty stable statistic. But you can see that ACE is not only representing the trend, but a lot of the year-to-year variability too. And the year-to-year variability here has to do with El Nino. So it's able to represent the forced response to El Nino. And in fact, if you look at the regression of a measure of El Nino called Nino 3.4, which is basically a temperature in the central tropical Pacific, deviation from normal, and you regress that on precipitation around the world, ERA 5, which is our reference, is down at the bottom. So that shows the pattern of precipitation response we hope that our emulator would reproduce with respect to El Nino. And then the emulator is shown on the top left. And you could hardly tell those 2 patterns apart. This is not an easy thing to predict right with a climate model. ACE does better than all climate models pretty much in this regard. Even if you didn't train it on the last 40 years, but if you, last 80 years, but you trained it just on an annual cycle of SST, you get the pattern that's on the upper right. So you do better, but ACE has got the right answer already to some extent, even before we start. Another thing we did with ACE then was we looked at the response to increasing CO2. So at this point, at the time we did this, we didn't have an ocean we could couple to. So instead, we used what's called a slab ocean model, which is just a thermodynamic version of the ocean, which can warm by taking in heat from the atmosphere and cool by removing it. This has the advantage that you can, if you add CO2 to the atmosphere, it can then cause the ocean to warm by the greenhouse effect, and you can measure how much and what the spatial structure of warming is. And we trained it on a couple of climates and then tested it for the amount of warming in an unseen climate, which is shown here. And basically, the pattern of warming here indicates whether the model has the right sensitivity to CO2 changes. And you can see, again, the pattern in the original model shown on the left and the pattern shown in with the emulator on the right for a 3 times CO2 increase is almost identical. Okay, so now Laura talked about Samudra, so I'm not going to talk about this anymore. Let's see, I have to get down in. But here I want to mention that, so the way we're going to use Samudra is slightly different than most of Laura's simulations. So she was mainly looking at a historical run of Samudra where it was forced by atmospheric reanalysis. And we're going to use it in a different way. But okay, first we have to get through this. These are all things Laura talked about. Another important thing about Samudra, though, is it didn't predict sea ice. Basically, started with forcing actually under the sea ice and regions of sea ice to force the ocean. Okay, so now we're going to then talk about what we did to couple Samudra to ACE. So here, what we do is we take Samudra, and we're going to force it with ACE atmospheric fluxes at each location. And similarly, then we're going to force ACE with Samudra's sea surface temperature. So this is the way that they're coupled. We had to introduce interactive learned sea ice. And in order to train these 2 emulators, we used 160 years of a run of a climate model called CM4 that was developed by GFDL. And basically, what we do is we first just use the reference data from the atmosphere to train the ocean, to train Samudra. And then we use the sea surface temperatures from the reference ocean to train the atmosphere. So now we have these 2 pre-trained emulators, and then we fine-tune them together to make a coupled emulator. And we test this on 40 unseen years of this run. The inference is stable without climate drift, and it works. And it runs 1,500 years per day on a GPU. So just to show you what the process looks like, I'm not sure how I'm doing for time. 5 minutes, okay, that's good. So as I mentioned, we have this uncoupled emulator where we give it uses 5-day updates from the ocean. So recall, Samudra uses a 5-day time scale. Our atmosphere model ACE uses a 6-hour time scale. This reflects basically the internal time scale of variability of the atmosphere being much faster than for the ocean. It's a lot easier to learn a system on its natural scale of variability than if you try and learn it on a scale that's too short or too long. So we feed all the ocean for 5 days into the atmosphere. And then for the uncoupled ocean, then we're taking the atmosphere, we take the average of the 5-day fluxes, the atmosphere is rolling out in 6-hour time chunks, and then we feed those into the ocean. And then in the coupled setting, we kind of have each component talk to each other in the way I was talking about. So here's an example of a rollout of the coupled emulator. So all I'm showing here is the averages over successive months. So there's a lot of variability in the sub-monthly timescale that's not shown here. But one thing you can see is the white on the top, for instance, is the sea ice expanding and contracting with the seasonal cycle. And if you look at the temperature, say in northern Canada is fluctuating from yellow to purple. That's the annual cycle of temperature over land, warming in the summer and cooling in the fall. And if you look carefully, then you can also see changes in the ocean. Changes are not exactly the same from year to year, but they reflect, again, a large annual cycle. And you can keep this going indefinitely. Okay, so if you couple these two emulators together, then the time mean biases relative to the reference CM4 simulation are actually quite similar to the uncoupled component emulators, and they're quite small. So for instance, this is the precipitation bias, the time mean precipitation bias away from the CM4 reference pre-industrial simulation for the emulator. So this is testing the atmosphere. And this precipitation bias you would kill. If you could get a climate model that was this accurate, you would say, I'm in heaven. So it's working really well. Similarly, if you look at the ocean surface temperature bias relative to the reference from CM4, the root mean squared error is 0.33 degrees K. Again, you would kill to get a physics model that does this. So the emulator is really doing a good job of capturing the mean climate of the reference model. It also does a good job with the sea ice. As I mentioned before, the extent of the sea ice is changing in the right way from time to time across the seasons. And the most important thing, actually, though, is it's able to reproduce coupled variability. So in particular, El Nino is the most important coupled mode of variability between the atmosphere and the ocean. It spontaneously forms due to feedbacks between the two components. And so it's a really good test of an emulator, and it's really hard. Other attempts at making coupled emulators have failed to get realistic ENSOs. And we're coming pretty close. So if you look here, this is Nino 3.4, which is a measure of El Nino in the original coupled simulation over the 40 unseen years. And the blue indicates our emulator. And you can see it has the right period of variability. The amplitude isn't quite large enough. Here's another attempt at this, the so-called DLE-SIM model. And it gets weaker variability than we get, although it's trying to do the right thing too. And again, within this coupled system, we're still able to get the right precipitation response to El Nino. So the spatial pattern of variability is right. What we don't get is good low frequency variability here. At timescales longer than 3 years, we get less variability in Nino 3.4 than we should. So it's still not perfect. Okay, fine. So other things are good. Our overturning circulation, which is a measure oceanographers care about, is nice. And let's just get to the final challenges. So, okay, so challenges in this: training data. Like how much training data do we need? Could we get low frequency variability if we used a longer sample of training data from the reference model? Can we combine observational and model data? we had a lot of problems with masking, with where the land, ocean, and atmosphere are after you have different models and different interpolation strategies. And out-of-sample generalization is still an issue. Okay, so I'll just leave my conclusions up here. Basically, I think the main point is we are now able to start attacking coupled modeling as an emulation problem fast. We're heading toward making emulators that I think can do things like CMIP simulations with changing climates. And these emulators are super fast, so they're quite attractive for a lot of applications that involve ensembles of simulations. Okay, fine. Here we go. You can read my conclusions, and we can take any questions if there's any time.
Hi, thanks for a good talk. So I was just curious, you have talked a lot about training on reanalysis and training on climate models, but both reanalysis and climate models do have biases in certain places. I'm thinking about like over the Southern Ocean, for example. Do you see a path forward to be able to incorporate like more like actual MODIS data into a setup like this somehow?
Yeah, so there are, reanalysis has the virtue for this purpose of being internally consistent. And so the problem with data sets like MODIS are if the data set only is available some of the time, for instance, can be hard to incorporate into training, because like how do you train an autoregressive model on data which you don't have every 6 hours, for instance? Now, I think it's fair to say also that data sets like ERA5 reanalyses are becoming increasingly sophisticated in how well they can reproduce satellite observations. So the reanalyses are improving. But I would also say that in the weather sphere, now the big push is to what's called end-to-end modeling, where you basically go straight from the data to the forecast. And I don't know that that can easily be taken advantage of here for climate, but it is a new development. It's actually, that can work quite well too. And so it's not the case that AI models are somehow intrinsically forced to work on grids in the way that we have done.
So that with the, being able to do ensembles this fast and everything in terms of like the policy angle and the use of all of these simulations, I mean, where do you see, like, what are some of the big questions that people would have loved to have been able to answer or address before that were completely unavailable that now are, that you're like most interested in?
Well, so large ensemble of coupled climate simulations are sort of actually a staple of what we use right now to do IPCC assessments. And so, for instance, a model like NCAR or GFDL, a coupled climate model, will typically run an ensemble of 50 simulations, into the future, each, 100 years or more. And the big problem is actually that is consuming a huge amount of computer resource, HPC resource right now. It can be consuming a third or half of their computing budget for long periods of time. And so in some sense, it already represents a giant wasted resource. And of course, we can make those ensembles larger. I think there's still some questions about whether the ensembles are accurate enough to be used that way. But and another thing is that I haven't talked about it here, but another application of models like this is they can be very convenient for doing what's called downscaling. So people are very interested in local climate information. For instance, we've worked with people from Singapore. Singapore is a tiny little island. They don't care what's happening 500 kilometers away. They want to know what's happening over their tiny little island. And so they spend, again, huge amounts of computer time taking a few of these ensemble members and then trying to translate that information using another detailed model down to information on the scale they care about, which is, the kilometer scale information. Turns out we can do that with machine learning, with generative machine learning, really well with diffusion or flow matching. And so, and it can slot very nicely into this procedure. And so again, we could save people a lot of time, make their job a lot easier. And so there's already a lot of interest in the community on those kinds of uses, just like making people's lives simpler and faster. So it's not transformational in the sense of new science, but it is transformational in the sense of accelerating existing crank turning that wastes a lot of time.